Good day, I'm Dr. T and welcome to my office. So today I'd like to talk about pH. pH is really a way of describing the concentration of hydrogen cations. Well, I should say hydronium ions, but they're hydrogen cations. Hydrogen cations don't actually exist as H+, just floating around free. They're always going to piggyback on something, and when they piggyback on a water molecule, we call it a hydronium ion, H3O+. That said, everyone just usually thinks about them as H+, and yeah, I'm going to keep doing the same. Okay, so when I look at this, I want to look at a solution. If I have water, I'm always going to have some H+. The water itself will split apart, and it will form OH- and H+. Given nothing else in the mixture, at normal temperatures, you're going to see something like 1 times 10 to the negative 7th molar H plus and the same amount of OH minus. And that's what we consider neutral. Yeah, that's a lot of zeros. However, if I add an acid, I can get that all the way up to 1 molar or above. It's difficult to go much above 1 molar H plus. Usually the acid doesn't quite dissociate. But still, once again, that's a lot less zeros. That's a pretty big range. If I add some strong bases in there, I can easily get down to, well, not so easily, it's a bit of a challenge, but I can get down to, say, 1 times 10 to the minus 14th molar H+. Wow, these are a lot of zeros. This is a huge range. You have literally 14 orders of magnitude going on over here. Yikes. So the way we deal with this is we're going to do a negative log. We're going to do a log, the log version. This is a base 10 log, not the ln, which is a base e version. We're going to do a log, which is going to then, instead of having, say, 1 times 10 to the negative 14th, it'll be negative 14. You take the number in scientific notation, assuming the coefficient is 1. If it's not 1, you have to change it so it is, which gets really trippy for the math. But you change the coefficient so it's 1, and then it's whatever your exponent is, that's your log. Now, because we'd be dealing basically exclusively with negative numbers, we take the negative log. That way, we just get rid of that negative sign. So instead of having negative 14, we just say it's 14. Now, taking the negative log is referred to as the power of, and thus, p. By the way, that's a lowercase p, so you can't start your sentence with the word pH. I know. The H, well, that's the hydrogen. It's the power of hydrogen. You can do P other things. You can do POH. That's the power of hydroxide. And that will actually be a mirror image of the hydrogens. So the pH plus the POH will always equal 14 for normal water. If it's not water, well, you probably shouldn't be using pH to start with. And the numbers don't quite add up to 14. They add up to something differently. And once again, you probably shouldn't be using pH because that really strongly implies water. Okay, so we have this negative log thing. Now, what if I want to go backwards? So going forwards, I simply take the negative log of whatever my hydrogen cation concentration is. Yay! What about going backwards? Let's say the pH is 6. How do I get that into the hydrogen cation concentration? Well, if you look at your calculator, you almost certainly see right above your log function a function that is 10 to the x. You simply take your pH, put the minus sign back. So if it's pH of 6, then you take negative 6, and then raise 10 to the power of the negative 6. Then boom, 1 times 10 to the negative 6 molar H+. Yay! This works fairly straightforward. Now, for reference, what some of these pHs represent, any pH that is below that of 7, because if remember I said pure water, the amount of hydrogen would be 1 times 10 to the negative 7th molar. So any pH less than that, which would indicate that there was a higher amount of H+ present in your solution. I know that is really trippy and it trips me up a lot. But any amount that's greater than that would result in a pH that is lower than 7, and that would be done by having an acid. So those solutions are acidic. pH of 7, we call that neutral. By the way, temperature does actually affect where these numbers fall as far as what true neutral ends up being. Yeah, just to make life interesting. But pH of 7, that's for normal temperatures. Yay. Now, if your pH is above 7, that means your hydrogen ion concentration is less than 1 times 10 to the negative 7th. I know. And that means you have a base in there, something that's sucking up H pluses. So in that case, anything above 7 is going to be basic, or alkaline is another way of saying basic. I should point out that your pH range usually stops at about 14. At this point, you start doing weird things with water, and you're not going to be able to get a pH above 14 in an aqueous solution. It's actually really hard to go much above 13. And you can switch over to like an alcohol, then you can get a 15, but it's not really a pH because you're not in water. Additionally, it's particularly difficult to get a pH much less than 1. You can definitely do it. All of a sudden, really the numbers stop meaning as much as they did before. You're starting to get to the point where even your strong acids aren't fully disassociated. Which actually leads me to a quick point on strong versus weak acid. Strong versus weak does not mean concentrated and dilute. The pH start giving you a nice description of the H plus concentration, but especially if you have a weak acid in there, you can still have a fair amount of that in reserve at a specific pH. So concentration, pH, strong versus weak are all three actually independent things that you can run into. So let's talk a couple other cases. If you're looking at fruit juices, those are going to be on the modestly acidic side, so a somewhat lower pH. If you're looking at human blood, you're looking at a pH of pretty close to 7.4. You actually run into a scenario where the proteins that are responsible for sustaining life have to have a very narrow pH range for them to be able to function. So human blood needs to be within 7.35 to 7.45. Otherwise, you're basically dead. Actually, at those extremes, you're in pretty bad shape. So you have a very tight control of human blood. Now, when it comes to pH, quite often we do want to tell what that is. We have a couple of ways of determining pH for a solution. The first and kind of the most popular for just casual use is going to be the use of indicators. Indicators are going to be chemicals that are chromophore, meaning they're capable of absorbing light, and a weak acid or a weak base. So if you recall, weak acids, weak bases are in equilibrium with how many protons they pick up or let go. The pH is describing the concentration, so at some pHs your indicators will pick up protons. At higher pHs they will lose their protons. Now, for these indicators, the presence or absence of the proton will, by extension, affect how they function as a chromophore, so it'll change their color. And thus, by knowing what color they are, you can get an idea of what pH they are. Sometimes you can use a blend of indicators to get a much better idea. In other cases, you have one, and it simply tells you are you above or below a certain pH. Now, if you would prefer to go a little bit more high-tech, we can use a pH probe, and in that case, you have what is effectively an electrochemical cell that has a porous glass membrane that allows the transitioning of H+ across the barrier that it creates. The moving of charge is, of course, an electric current, and thus by measuring the ability for that electrochemical cell to function, you are then able to determine what the pH of the solution it's dipped in is. So yeah, pH, one of those interesting facts of life you run into over and over again. So with that said, have a wonderful day. I'll see you in later videos.